Hi, my name is Fee and I am excited that you have found this tutorial. Perhaps you are aware that one of the fascinating stories told through data can be found on the Gapminder website, where we observe the evolution of the relationship between a country's life expectancy, gross domestic product per capita, and its population. Let's go on a journey to explore how to prepare data for analysis using our statistical programming language. We will use datasets from this website and learn functional techniques for preparing them for analysis. I love how R handles data, and I hope you will enjoy it too. There are at least two compelling reasons to enhance your abilities in preparing data for analysis. Speedy data processing leads to faster insights. Real-world data is often messy and sourced from multiple channels, so it must be refined to be analyzed. Improving your data preparation skills can reduce the time spent cleaning the data and increase the time spent gaining insights. Our goal as data scientists or analysts is to gain meaningful and practical insights from data. Creating top-of-the-line models to solve business problems is important. But to ensure rich and accurate insight, data preparation is key. It's essential to keep in mind that the quality of data analysis depends on the quality of the input data. Poor inputs leads to unreliable results. This tutorial aims to help you enhance your data preparation and manipulation skills using the functional tools available in the R statistical programming language. With R installed, I will be using RStudio as the integrated development environment for writing my R code. You can download and install a free recent version from the POSIT website. If you do not have RStudio IDE or prefer using a different IDE, it is perfectly fine. To follow along, you can use either R Markdown, Quarto, or RScript. In case your RStudio version does not come with Quarto or you are using a different IDE like Visual Studio Code, you can download Quarto from their website and install. To get the files for this tutorial, you can either clone the repository or download the zipped file from GitHub. If you are using RStudio, you can go to File, then New Project, then Version Control, and finally Git. Paste the Git URL for this repository, choose the directory for the project, and create it. In the project folder, you should find a begin file where you can author the code and an end file to check for the solutions or the final code in case you get stuck. I presume you have a basic understanding of the R programming language and have worked with data structures like data frame, list, character vector, and function before. Some familiarity with the tidyverse package, particularly the dplyr and purrr component, would be helpful, but I will explain the concepts in simple and clear manner so that even a beginner can follow along easily. We will use R version 4.2.2 and incorporate functions from the tidyverse package. The tidyverse package offers a straightforward and efficient method of working with data, but I have also included the equivalent base R code in the end files. You can compare and contrast the two approaches. You can install the tidyverse package by running in your R console install.packages with the string tidyverse as an argument. When done installing, we can attach tidyverse to our search path so that unless there is a name conflict, we can avoid including the package name when referring to its objects or functions. We will use the library function to load the tidyverse package, which includes several other packages like readr, dplyr, and purrr. For simplicity, we will require the entire tidyverse suite, instead of loading individual components separately. We will be using Tidyverse version 2.0.0 in this tutorial. There are two important inquiries you may make on any attached package. The first inquiry is to understand what objects and functions the package contains. For instance, you can find out what functions are included in the readr package by running ls package readr. This will show you the various functions for reading and writing data such as read_CSV and write_RDS. The second inquiry is to understand what a function does and how to use it. To access this information, simply run in the console $ followed by the function name. This will give you the documentation for the function. If you want to know more about the package, including the purpose and how to use it, you can read the vignette that comes with the package. This is what we will learn if we journey together. We will explore efficient methods of working with multiple files or data objects using functional tools provided by the purrr package. This will eliminate the need for traditional for loops and allow us to accomplish more tasks with compact and maintainable code. Also, we will construct functions to handle various stages of data integration. This will not only make our code clear and readable, but also make it easily reproducible. The functions we will create and the knowledge we will acquire can be applied in future data preparation projects. Let's start. In order to bring data into R, it is important to first understand where the data is located and what format it is in. Data can come from a variety of sources such as the web, a database, or a local computer, and it can be in different file formats like CSV, JSON, or even Microsoft Excel. Knowing the location of the data and its format is crucial in establishing the connection and loading process. In our case, the data files are stored on our local computer. To see what is in the current working directory, we can use the dir_ls function from the fs package or the list.files function from base R. The fs package provides a convenient way to handle file system in R, but you can use either approach to list the contents of the current working directory. I have the fs package installed, but have not attached it to my search path, so I am using the : operator to access its dir_ls function. The files we will work with are contained in the data subfolder of the current working directory, and we can list its content by specifying the data folder as the path argument of the dir_ls function. The data folder contains 3 separated value files: GDP, life expectancy, and population. We will reuse the file names later, so let us assign or bind to a variable we will call CSV_files. To gain a better understanding of the data unification process, we will start from scratch. We will read the datasets, understand their structure, and then unify them. Instead of following a preconceived script like this one, we will form our own hypothesis about the data and justify each action we take on the datasets. This will help us build valuable skills and have a deeper understanding of data manipulation using R. So do not worry if you don't fully understand this piece of code, which can be used to read and unify the 3 datasets. We will unpack it later with detailed explanation. It is important to note that instead of reading each file individually and hence create multiple variables and repetitive code, we can use functional techniques to iterate over all the files avoiding for or while loop. To give you an idea of what we are trying to achieve, let's read in the GDP dataset using the read_CSV function. Here, we also specify the full path of the file. This will give us the content of our gdp.csv file as a table, a special type of data frame used by the tidyverse package. This rectangular data contains 195 rows and 252 columns, with the first column representing the country name and the rest capturing the GDP per capita for each country starting from 1799. If we want to suppress the column specification message, we can set the show_call_types arguments of the read_CSV function to false. However, let's do the suppression at the global level for this R session using the options function and requiring that the show_call_types variable of the readr package should be false. If we read the data again, we do not see the specification message, and this will be the case whenever we read a file during this R session. We learned that the read_CSV function is capable of reading a single .csv file. However, to read all the .csv files at once, the read_CSV function needs to be vectorized. This means we can pass the entire CSV_files vector to the function. Unfortunately, this results in an error because the function requires that all the datasets have the same number of columns. In this case, the GDP file was the first item in our CSV_files vector, so it uses that as the baseline to require that all the datasets must have 252 columns. To use the read_CSV function on multiple files, we first need to make sure that the datasets have the same number of columns. The life expectancy and population datasets have same columns and are positioned second and third in the CSV_files vector. By using the read_CSV function on just these two datasets, we can successfully read and merge the datasets into one, where the final dataset's number of rows is equal to the sum of the number of rows in the individual datasets. However, we cannot distinguish which row belongs to life expectancy or population. To solve this, we can use the ID argument of the read_CSV function. This argument allows us to add a new column where the value is the file path, telling us the source of a record. In our case, let's name this new column Origin. This way, we can differentiate between the two datasets by looking at the value in the Origin column. The takeaway from this is that if you have multiple files with matching columns and you want to merge them by rows, then the read_CSV function can be useful. Just be sure that the data in the files have the same columns. You can also specify an ID argument to include the file path or source of the file as an additional column for record differentiation. Let's take a different approach to reading our files, one that doesn't require prior knowledge of the structure or dimensions of the dataset. We will use the map function from the purrr package, which is part of the tidyverse package. The map function will allow us to apply the read_CSV function to each element or file name in our CSV_files vector. This technique of having a collection of items and applying the same function or operation to each item in the collection is a powerful technique and can be used as an alternative to for loops in R. Essentially, we provide the map function with the CSV_files vector and the function to be applied to each element in the vector. The result will be a list of 3 data frames, specifically list of tables, a special data frame used in the tidyverse ecosystem. If you are following along using either Quarto or R Markdown and the printout does not clearly look like a list to you, you can try the code out in your console for confirmation. If you are familiar with the apply family of functions in base R, the lapply function works similarly to the map function. We can write the code using the pipe infix operator, %greater than %. This operator takes the result of the expression on its left and passes it as the first argument to the function on its right, unless there is a placeholder. Using the pipe infix operator allows us to chain multiple steps together and write our code as a series of sequential steps similar to a recipe. In this case, we take the csv_files vector and pass it as the first argument to the map function. However, I must say that using the pipe operator is more compelling when there are multiple steps involved. The result of this operation can be stored in a variable, for example, DFS. Here is a useful tip to further enhance your understanding of the concepts discussed so far. If you are looking for a fast way to read delimited files, consider using the fread function from the data.table package or the vroom function from the vroom package. In addition to being fast, the fread or vroom function can auto-detect the separator or the delimiter of the file. The read_csv function uses the vroom function under the hood for faster file reading, and you can verify this by scanning through the function body in your console. Here are some challenges to test your understanding and get you to apply the concepts covered in the tutorial. If you need assistance, the solution can be found in the end.qmd file or end.rmd or end.rscript included in the cloned or downloaded files. Use the read_csv function to access the GDP dataset directly from the GitHub repo. This is the GitHub URL. Also, using the URLs of the three files, life expectancy, population, and GDP, read them as a list of data frames using the map technique discussed in the tutorial. This time, your datasets are 3 remote CSV files hosted on GitHub. When reading the CSV files in the data folder, we listed the files and stored to a csv_files variable. To avoid this step, utilize the dir_map function from the fs package to directly apply the read_csv function to all the .csv files in the data folder. Remember, you can check the end files for the solutions to the challenges. Good luck. The names of our list of data frames, DFS, after applying the map function, were read from the names of the csv_files vector. It is important to note that if your csv_files vector was created using the list.files function from base R, the names attribute will be null, and your list of data frames DFS will be numbered instead of explicit names like data/gdp.csv. We can make the names of the list of data frames in our DFS object more readable by removing the .csv extension and the data directory. This can be achieved using the setNames function, which allows us to set the names using the elements of our csv_files vector. However, the str_remove_all function is utilized to remove both the data directory and the CSV extension. Basically, we have provided the str_remove_all function with the string or character vector and the regular expression pattern to remove. The vertical bar alternation operator in our pattern matches either one of the two elements being compared, data/or .csv. This approach of using the CSV_files vector to set the names of our list of data frames works even if the list of data frames DFS had no names. Upon checking our DFS variable, we will find that our list of datasets now have names with the directory and file extension removed. Once again, if you are following along using either Quarto or R Markdown and the printout does not clearly look like a list to you, you can try the code out in your console for confirmation. Observe the sequential order of steps through the use of the pipe infix operator. The CSV_files vector, which holds the paths to our datasets, is used as the starting point. Then we apply the read_CSV function via the map function to read all the files as list of data frames. And finally, we set the names of the list by utilizing the CSV_files vector, but removing the .csv extension and the data directory. There is a wide use of the base R pipe operator vertical bar greater than within the tidyverse community of late. In the earlier code, for instance, we can replace the %greater than% with the vertical bar greater than and achieve the same result. Our aim is to merge the three datasets into a single data frame. In order to do so, it is important to ensure that the datasets have consistent characteristics such as an equal number of columns and matching column names and types. Let us focus momentarily on the GDP dataset and take a glimpse to display the structure horizontally. We see that the country column has the correct data type, character, but some of the year columns have the incorrect data type. They are of character type instead of numeric. This is an issue because we need the GDP to be numeric in order to perform arithmetic operations on it. Knowing the data types of the columns is critical because it defines what type of computation we can perform on them. To make the process of checking data types more formal, we will extract the GDP data frame from the list of data frames, either by using the plug function or the $sign operator. We will then select all columns except the country column, as this column already has the desired data type. In other words, we will use the -unary operator to deselect the country column. Using the map_chr function, we will apply the typeof function to each of the remaining columns to get a sense of their data type. It is important to note that a data frame can be treated as a list, with each column being an element of the list. This allows us to use the map function on a data frame. The map_chr function is a variation of the map function. It is used when, instead of a list, returning a character vector is convenient. Take notice of the chr suffix, which means the output is a character vector. In this case, we aim to get a simplified and unique representation of the data types of the columns in the GDP data frame. With this approach, we can quickly identify any mismatches in the data types, such as when some columns are of the numeric or double type while others are of the character type. This is a more straightforward method to understand the data types than using the glimpse function, which can present a lot of information that requires scrolling and scanning. There are variations of the map function one may use whenever the applied function returns a vector of length 1. The type of the vector is determined by the suffix to the map function. For instance, the suffix int in map_int function means the output is a vector of integers. The typeof function provides the internal data type or storage format of an object in R. For instance, a factor object in R is stored internally as integers, so using typeof on a factor object will return integer. Also, using typeof on a data frame will return a list. The class function, while also useful, can have its limitations. For instance, the class of an ordered factor is a character vector of length 2, which is not a unique class. It is important to have a consistent method to identify data types. If we want a more user-friendly and recognizable representation of data types similar to what is displayed by table, we can use the typesum function. This gives us a brief summary of the object type. We expect every year column to be numeric since we are talking about GDP of countries, and we can explicitly check that. We use the every functional tool and provide the is.numeric predicate. This, as expected, returns false since not all the columns are numeric. Some are of character type. To make the process of knowing the data types of columns more convenient, we can create a function called getCallType that takes a data frame as input. This function will perform the steps outlined earlier by applying the typesum function to every column in a data frame. By using this function, we will be able to quickly and easily determine the unique data types of columns in any data frame. We will apply this function to the list of tables, DFS, by first using the select function inside the map function to exclude the country column. Then we will apply the get_call_type function to the remaining columns. We see that the columns have different data types. For instance, the GDP dataset is a mixture of double, thus numeric, and character data types. The population datasets, on the other hand, had the columns recorded as character type. Notice how the select function is written inside the map function as part of a shorthand anonymous function. Whenever the function you are applying takes additional constant argument, as in the case of our select function, which first takes a data frame and then the columns to select as additional argument, it is recommended to use anonymous function approach instead of the ellipsis approach to make it easier to understand which arguments belong to which function. With the ellipsis approach, one can be misled to think country is an argument of the map function. Another approach is to write a one-sided formula. In this tutorial, unless otherwise, I will stick with the shorthand anonymous function. We just replace the word function with a backslash, and it is called an anonymous function because we did not bind it to a variable for reuse. In other words, the function has no name. To merge or reshape our datasets, we need the columns to be of the same type, and by the hierarchy of data types in R, coercing double to character will not result in missing values. So let's do that. We will create a function called mutate_as_char, which takes a data frame as an argument and transforms via the mutate function all non-character type columns to character data type. We will use the across function to select all non-character columns and apply the as.character function to each of them. Realize that the is.character predicate is written inside the where function, which helps in using a predicate function in selecting a variable. The unary negation operator negates so that the test works on only non-character columns. We can now confidently use the mutate_as_chr function on our list of data frames to convert all columns to character data type. Let's go ahead and also apply the get_call_type function we wrote earlier to confirm if for each data frame we have successfully coerced all columns to character. Everything looks good. Ensuring consistency in the data type makes it easier for us to later perform data merging and reshaping. You have heard me use the term predicate function. It is a technical term for a function that returns either true or false. For instance, is.integer32 will return false, and that makes is.integer a predicate. If getting false for this example confuses you, add uppercase L to the end of the number and see the result for yourself. Let's use the modify_if function from the purrr package to handle the task of converting non-character columns to character. I will later show you why you may consider this functional approach instead of the mutate function we used earlier. We create a function called modify_as_char, which takes a data frame, and if it identifies that a column is not of character type, it modifies it to character. Take notice of how the is.character predicate is negated using the negate function to ensure that we modify a variable only if it is not a character type. We iterate our modify_as_char function over the list of data frames, and to test if we have character type after the modification, we can use the getCallType function we wrote earlier, or my preferred approach, we test if every column is of type character. We get true for all the data frames, indicating our modify_as_char function works as expected. Take notice of how the every function is written as an anonymous function because it takes additional constant argument, is.character. Now we have two functions that accomplish the same task. One reason you may prefer the modify_as_char function to the mutate_as_char function is that the former uses a functional tool from the purrr package and it can be faster. We can quickly use the microbenchmark function from a package of the same name to establish this. We write the two expressions separated by comma, the mutate approach and then the modify approach. Let's evaluate just 5 times. We see that per my computer, the modifying approach is relatively faster since it accomplishes the computation in less time. We will go ahead and coerce all columns to character and reassign the DFS variable. Instead of mutating the columns to character type after reading the files, what if we set the column data type as character right at the time of reading the files inside the read_CSV function? To achieve this, we can take advantage of the call type arguments in the read_CSV function. By setting this argument, we can specify the data type of each column in the input file, allowing us to enforce a consistent data type right from the start. Try it out. To learn more about this call types argument, it is recommended to read the documentation on read_CSV function. We will now convert our data frames from a wide format where the years of record span multiple columns to a long format, thus a single year column. We can achieve this using the pivot_longer function, which, as the name suggests, pivots data from wide to long format. To do this, we will reshape all columns except the country column. For each of the datasets, this results in a reshaped data frame with 3 columns: country, name representing the years, and value column. Let's change the name column to year to provide a clear and specific label by setting the names2 argument of the pivot_longer function to the string year. I have intentionally used a one-sided formula here when specifying the pivot_longer function that takes additional arguments. This way, you can have a feel of it. The tilde or twiddle symbol is what makes it a formula, and the .x is a pronoun that stands in for the data the pivot_longer function takes. It is important to note that if we had not made all the columns the same type by mutating them to character type, using the pivot_longer function would have resulted in an error, since the function does not know how to combine columns of different types. Instead of using the map function, we could use the map_dfr function, which would result in a single data frame by combining the dataset row-wise, and also set the .id argument to say origin, so that we can have an extra column that will differentiate each record as GDP, life expectancy, or population. This works because the list of data frames DFS is named, and its names are used as the entries of the newly created origin column. If the list of data frames were unnamed, the index of the elements in the list would have been used instead. Though the map_dfr function works, it is being superseded. Instead, it is recommended to use a combination of map and list rbind functions. Inside the list rbind function, we can set the names_to argument so that the names of our list of data frames can be used as additional column for record differentiation. Another approach we could take to differentiate each record is, prior to merging the dataset, we add a column to each of the datasets to indicate whether a record is GDP, life expectancy, or population. Let's do this, since it will allow us to further explore the functional programming tools offered by the purrr package. We will go ahead and only reshape the data frames from wide to long format, and exclude the row binding step. Let's create the function add-on call that will add an extra column to our data frame with a specified value. The function will take two arguments, a data frame df and the desired value for the new column. We will use the mutate function to create the new column and name it origin. I will later demonstrate how to modify the function to accept any desired column name instead of the hard-coded origin name we have. We utilize our add-on call function by passing it two arguments, the data frame and the desired value for the new column. Our aim is to indicate the nature of the data contained in each data frame, whether it is related to GDP, life expectancy, or population. For example, when we apply the function to the GDP data frame, the new column should have the string GDP as its value. Similarly, for the life expectancy data frame, the new column should have the string life expectancy, and for the population datasets, the new column should have the string population. We can use the names function on our DFS variable to obtain all the necessary values we want to use to add-on the data frames. We have a list of data frames and a vector containing the values we want to add to a data frame as a new column. Instead of using the map function, we will use the map_to function. The number 2 in the function's name indicates that the function we want to apply takes two arguments, and we will iterate over both of them. We will pipe our DFS as the first argument and the names of our DFS variable as the second argument of the map_to function. In this case, the add-on call function takes the first data frame in our list of data frames and adorns a column with the first item in our names vector as the value. This process is repeated for the second and the third items. Run it and we get an extra column called origin for each of the data frames. This column will indicate if a record is related to GDP, life expectancy, or population. There is a shorthand for instances where the map_to function is used on an element and its index. Thus, the imap function, In our case, there is a list of data frames DFS and the names of the same list DFS. This means we can use the IMAP function. We can apply our add-on call function to the list of data frames DFS via the IMAP function without worrying about the names part. It knows to add on the data frames with the appropriate source. To unify the datasets, let's use the reduce function, and as the name suggests, it will take the 3 items in our list and reduce to 1. However, the function we will use to reduce the list of data frames into a single data frame is the union function, which is a set operation that takes a pair of data frames and combine them row-wise. We will assign the result to a new variable, df. This is what we want to achieve, the datasets unified as one. The pmap function, read as parallel map, is a generalization of the map2 function that iterates over multiple arguments simultaneously. Use it instead of the map2 function to apply the add-on call function to mutate the list of data frames DFS. In summary, we transformed our list of data frames into a single data frame by following these steps. Converted all columns to character data type to ensure compatibility with the pivot longer function. Used pivot_longer function to convert the wide format to a long format, collapsing all columns except the country column. Created an extra column using the add-on call function to indicate the source of each record, either GDP life expectancy or population. And then, we reduced the data frames row-wise using the union function. However, there is no compelling reason to go through these steps when the same result can be achieved using either map_dfr function or a combination of the map and list_rbind functions. Let's make a slight modification to the add-on call function. Instead of having a hard-coded column name, we can allow the user to specify the new column name. To do this, we add another argument to the function called call_name. In the mutate part of the code, we change the hard-coded name origin to the value of call_name and embrace it in double parentheses. We replace the equal sign with a dynamic dot. Whenever datasets are unified or reshaped, there is a possibility of introducing missing entries, even if the original datasets do not contain missing values. To test for the presence of missing values, we can use the any_na function from base R. This function returns true if there is a missing value and false if there are no missing values. To find individual missing entries, we can use the is.na function, which returns a boolean or logical array. The sum of this array will give us the count of missing values. Let's make the process of counting missing values more interesting. We can create a function called count_na. This function can be applied to each column of the data frame via the map_dfr function to determine the number of missing entries in each column. We find that the value column is the only one with missing entries, with a total of 2079. To make the result easier to read, especially when we have many columns, we can reshape the data frame into a long format and use the everything helper function from tidyselect to reshape all the columns. This way, the result is displayed top-down rather than left-right. Now, we know that our data frame, specifically the value column, has missing records. Usually, we want to know the rows in our data frame where values are missing so that we can decide on what to do, perhaps delete them if we have a good reason to do so. Also, if we identify that there is a pattern to the missing records, for instance, they only occur on specific dates, then we can investigate further if there is a system failure on those dates or if there is a hiccup in the data collection process. To determine the rows in our data frame that contain missing values, we can use the ifAnyHelper function together with the filter function. This function allows us to filter records where there is at least one column with a missing value. Thus, we apply the is.na function to all the columns, and if any has a missing entry, that row is filtered. Though we could have relied on our knowledge that the value column is the only column with missing values, and thus condition our filtering on just that column using the ifAnyHelper function and considering every column is a more general approach. There are 2079 rows with missing values, the same as the result we had when we used the countNA function. It is possible that these rows represent countries with no recorded life expectancy for specific years, and basic frequency counts of the origin column can address this suspicion. All the 2079 missing records are life expectancy related. For each country with missing life expectancy, we can establish if the NAs occur on the same date. One way to do this is to nest on the country column. This returns a table with two columns, country and a data column, which is essentially a list of data frames containing the other three columns. We see the 9 countries with missing records, Andorra, Dominica, and the rest. They each have 231 missing life expectancy records. What is left is to establish if the content of the table is the same for each country. Just for clarity, we can decide to select only the country and year columns prior to nesting. If missing life expectancy occur on the same year for each country, then what is in the data column should be the same for each country, and that means we look for distinct entries in the data column. Since we get only a single record, we can conclude that the missing entries for each country share a common set of years. Note that the entries in the data column are the same not because the tables have the same dimension, but because they contain the same information. We can inquire from the data owners why the records are missing for just these countries and these specific years. Now, to deal with these missing records, we can either consult domain experts to come up with life expectancy estimates for imputation, or completely drop them from our data frame if we do not need those years in our analysis. If we choose to drop them, we can use the drop_na function, which leaves us with only the complete records. Note that removing records with missing values from a dataset can lead to a decrease in the number of observations available for analysis. This can negatively impact the conclusions drawn from the data, especially with a limited sample size datasets. Let's continue with our data cleaning. We will convert the data type of the value column from character to numeric in order to allow for numerical computations such as adding the GDP values for multiple years. Before converting the value column to a numeric data type, we need to ensure that the data is consistent and does not contain any letters or labels that could result in the creation of missing values. By filtering for population-related records, for instance, we discover that the population recorded in million has the label M appended at the end. This means that simply converting the value column to a numeric data type will produce NAs for cases where the numbers contain letter labels. To correct this, we need to identify all the different units used to label the numbers and take the necessary steps to resolve them. To deal with the different units in the value column, we will extract the non-numeric characters at the end of each value into a new column called unit. The \uppercase D in the regular expression pattern represents any non-digit character, while the dollar symbol indicates that we only want to match the end character. We will focus on distinct units, which may include no unit for purely numeric values or units such as K for 1,000, M for millions, and B for billion. The thinking is that if we remove the K's, M's, and B's from our values, we can successfully convert them to numeric. We can demonstrate this by creating another column called val, which will be the numeric version of the value column after removing the K, M, B characters. Realize that the pattern we are removing is enclosed in a square bracket to indicate the list of items we want to remove, K or M or B. It works, and we do not see a warning message indicating missing values introduced by coercion. This means to convert our value column to a numeric format, we need to eliminate the K, M, and B from the values. We will achieve this by creating a function label_to_num that takes in a vector of values. First, we will remove the K, M, or B from the values and obtain the numeric representation of the vector. The case_when function will help us determine what to do with the values depending on whether K, M, or B is detected. If a value ends in K, we will multiply by 1,000. If M is detected, we will multiply by 1,000,000. And if B is detected, we multiply by 1,000,000,000. And if none of these are detected, we will not make any changes to the value. The case_when function is used by providing a condition and specifying what actions to take if the condition is true, and you do that using a two-sided formula. You can find more information about case_when function in the relevant documentation. Note that the str_ends function detects if a given string ends in the pattern provided. If you do not want to use the case_when approach since it can be slow sometimes, and you are willing to think about the problem not as decision making but as data replacement, take a look at the end files and you should see another version of the label_to_num function, which is relatively faster, at least on my computer. The task is to find a solution to the problem of converting values in a character vector to numeric while considering different units K, M, B without using decision making as in case_when function. The solution should be achieved using only the str_replace_all function. The first step would be to read the documentation on str_replace_all function to determine how to use it to replace specific characters in a string. With this knowledge, one can then come up with a solution that solely uses string replacement to convert the character vector to numeric, taking into account different units. Good luck! By using the label_as_num function, we can now update the value column in our data frame to a numeric representation. This allows us to perform computations on the values. We will also modify the years as integers and the country column as factors. Let's now check the results of our cleaning. When we filter for records related to population once again, we can see that the value column now contains the numeric representation of the values and no labels. Some questions about the data can easily be answered if we reshape the data so that the GDP per capita, life expectancy, and population can have their own columns instead of all being under the origin column. We use the pivot_wider function for this task. The pivot_wider function will create new columns using the unique entries in the origin column as new column names and the value column as their values. This gives us what we want. However, since there are no fractional person, it is just appropriate to convert the population column from double to integers. Let's also assign the result to a variable df_wide. Using the count_na function we wrote earlier, find how many entries are missing, filter for records with missing values, and justify whether or not those records can be dropped. What have we done so far? We took CSV files, read them into R, combined them as a single dataset, cleaned it, and then reshaped to a desired format. Let's wrap each of the steps into customized functions, and you will know why momentarily. We write a read and combine function that takes a vector of files. We read the files as a list of data frames and then modify every non-character column as character. You have already seen these steps before, so there is nothing new. We bind our list of data frames as one and create a new column to indicate the source of each row by setting the names to arguments of the list rbind function to origin. Finally, we remove the data directory and CSV extension that appear in the origin column. And if we try this read and combine function out on our CSV files vector, we get the required result. Next, we write another function, reshape to long, that will transform our data frame from long to wide format, collapsing all the years as one column. In addition, we will convert the values to numeric by replacing the KMB labels that appear at the end of some values. Note that this achieves the same result as the label to num function we wrote earlier. Let's try this function too. We read our CSV_files vector and combine the datasets, and then reshape it into a long format. Nice! We get exactly the desired result. We will write one last custom function to reshape the data frame into a wide format so that GDP, life expectancy, and population can have separate columns. Also, we will transform the countries to factor and population to integers, putting all the three functions together via the pipe operator, read and combine, followed by reshaping to long and then to wide. We get the wide data frame we wanted. Now, what is the usefulness of using simpler functions to handle different aspects of data preparation? We can chain the functions together, and this can clearly explain the steps taken to prepare the data. If we will be doing similar data preparation on a similar data set in future, we can reuse our functions and not reinvent the wheel. Also, I want to demonstrate the compose function from the purrr package, which allows us to create a new function by combining multiple functions. We will call our new composed function preprocess_data. We supply the compose function our three functions in the reverse order, from last operation to first. The fact that we are specifying the steps backward means the function will be called from right to left, and that's a convention adopted from mathematics, which we will not go into. The read and combine function will be called first, followed by the reshape to long function, and then reshape to wide function. When we call our preprocessed data function on our CSV_files vector, we get the needed final data frame. We have successfully unified the three datasets and done some data cleaning. There are a couple of functions that come with the readr package that can help us write the data objects to file. If we intend analyzing the data with R, then it is recommended to save as .rds, which is R's file format and hence optimized for the programming language. For instance, in this case, the data types of the columns are preserved. Otherwise, we can save it as a CSV file or any other file format. The write_rds function takes the data or the object we want to save and then the file path. Running this piece of code will save the df_wide object in the current working directory as gdp_population_life.rds file. Go ahead and list the files in your current working directory or use the File Explorer in RStudio to see the saved file. We are now ready to use our data for exploratory data analysis. A simple task might be to describe China's GDP and life expectancy over the period 2000 to 2009. To address this, we take our cleaned data df_wide and filter for only the records where the country is China and the year is from 2000 to 2009. We only need the GDP and life expectancy columns, and hence we can select them. Finally, we use the summary function to obtain the distribution. For instance, the minimum GDP per capita recorded within the decade was 3,710, and the median GDP for the period was 5,660. If you take a look at the data types of the columns in our df_wide data frame, the two columns of interest, GDP and life expectancy, are of double type and the rest are not. We can use this knowledge to select a column provided it is of type double. Though we can use the select function to achieve this, I want us to use the keep function so as to broaden our functional programming toolset. We want to keep the elements in a list, thus columns of our data frame, provided a certain predicate or condition is satisfied. If an element is of a double type, we keep. Otherwise, we discard. We get only the GDP and life expectancy columns, and if we pipe that into the summary function, we get our needed results. The opposite of the keep function is discard. Thus, the discard function selects elements where the predicate evaluates to false. Implement the earlier code for finding the summary of GDP and life expectancy using the discard function. We can also go ahead and find out if there is a linear relationship, say, between GDP per capita and life expectancy. This time, we want to consider the two most populous nations, China and India. One way to do this is to split the data into two groups, one for each country, using the split function from base R. Since our country column is of a factor type and all the countries are part of the level, though we are dealing with China and India, we set the drop argument to true so that the splitting ignores all the other countries. This gives us a list of tables with two elements. We can apply the keep function technique to work with only the columns with double type. And for each of the elements in the list, we can ask for the correlation using the core function. The Pearson correlation coefficient for China, for instance, is about 0.984, which is very close to 1, and hence we say life expectancy tends to increase with increasing GDP. However, if the desire is to mutate the correlation between GDP and life expectancy as part of a data frame, then we can adapt this strategy. We group by the country column and then summarize each group by computing the correlation between GDP and life expectancy. This gives us a data frame showing a country and the correlation between GDP and life expectancy. Just so we get to use the map function inside a mutate function, instead of grouping by country, we can use the nest function to create a list of data frames of all columns except the country column. Complete the code to compute the correlation coefficient between GDP and life expectancy. The resulting data frame should look similar to what we had when we combined group by with summarize function. The linear relationship between GDP and life expectancy can be visualized via a scatter plot. Using the ggplot tool library, which is part of Tidyverse, we will create a scatter plot with the following mapping: GDP on the x-axis, life expectancy on the y-axis, and to distinguish which plot belongs to which country, we will set the color aesthetic to country. We add a point geometry to generate a scatter plot. This plot shows that GDP and life expectancy similarly trend in an upward direction. If the ask is to generate individual scatter plots for each country, then we can resort to the approach of splitting the data on the country column and then applying the ggplot function to each of them. We can write the plotting steps as a formula inside the map function. In order to show you another functional tool useful if we are only interested in side effects, let's assign the result to a variable plots. To get a printout, for instance, we can iterate the print function over the plot using the walk function. We get two separate plots, one for India and one for China. This process can be adapted even if we have more than two countries. Congratulations and great job for successfully completing the tutorial on data pre-processing and manipulation using functional approach. Remember that consistent practice is key to mastering any skill.